Okay, now we are ready. Also, the streaming setup was not correct. Now everything is set up, and we can start with the last practicals of object-oriented programming. And it's really nice to see a lot of you again. I think last time not so many of you were there, and today there are even more people here. This is very nice because we talk today about a lot of things which we find interesting about C++. So this is not really related to the lecture. It is also, most part is not presented in the lecture. We do this additionally. And I hope you find at least some of those parts as interesting as we do.
Yeah, but it's relevant for the practicals.
Yeah, indeed, it's relevant. So you also have a short homework on that, but we'll come to that. But just briefly outline what we have today. We start with organizational matters. We need to do this because yesterday was the assignment 2 deadline, and maybe that it's also in the recording and that you have heard it, what is going to be happen after the deadline. Then we continue very shortly about the lambda function we have discussed the last 2 times and never were able to finish. Then we have iterators and algorithms. So some parts were discussed in the lecture, but not a lot. Then we have some improvement on them and with ranges, views, and pipelines. This is a really interesting concept. And then we conclude with templating. This is something you've seen in the last lecture, and templating with concepts, which is a topic which we have never discussed before here. So let's see whether this works out.
Yeah, okay, so for homework 3, today we'll present a lot of new things, as you have seen in the introduction, but you also need them for homework 3. So we picked some of the things we do today, and we put very similar things often in for homework 3, namely, so you'll see templates and concepts, also lambda functions and algorithms, and then ranges, views, and pipelines. What all of this is, you will see later today. And yeah, so the deadline of homework 3 will be in 2 weeks.
3 weeks.
3 weeks.
Yeah, a lot
3
of time.
weeks. And it, as always, you just have to hand in a PDF file on the Teach Center.
Okay, so assignment 2. So now there are different cases that can happen. So if you submitted assignment 2 yesterday and you do not pass 25 test cases or do not pass this minimum requirement test case, then you are not allowed to register to the interview simply because you cannot pass the course. So please do not register to the interview and continue working on assignment 2. In the other case, if you pass 25 test cases at least and the minimum requirement test case, then you have actually 2 options. So you can also choose to not register to the interview and do the assignment 2 correction. So if you have like around 25 test cases, then it's probably better that you do the A2 correction. Or the other option is that you now register to an interview. So this will be, registration will be open today in the evening until Saturday. And then you do the assignment interview in the next week or the next 2 weeks. And then you're allowed to do assignment 3, but assignment 2 is over then for you. And we also have a recommendation. So the recommendation is for option 2, so for doing assignment 3, that you at least pass around 35 test cases, maybe a bit more, maybe 40 test cases. Why? Because assignment 3 depends on assignment 2, so you will extend your assignment 2 code. And if this causes a lot of troubles at the moment, then probably you will not do fine in assignment 3. So then, yeah, if you do not pass enough test cases, probably do the correction. So what is the correction? Okay, you have simply until the 12th of June. So this is again 3 weeks roughly. And you just continue working on assignment 2. And then you have the assignment interview after this deadline. But you can only do the correction then. So no assignment 3 for you. And in the other case, if you register to the assignment interview now, the registration deadline is then on Saturday in the evening. So please register as a group by Saturday to your tutor. And then in the next week or the next 2 weeks at some point, there will be your assignment interview. What are the tasks? You need to be able to explain all submitted code, and with all, I mean all, so also the code of your teammates. It's not enough that you only know the third of the code that you have written. You really need to be able to know everything of the code. You don't need to know every little detail, but you need to know what is happening there. And additionally, there is also a coding exercise at the assignment interview. So you'll get a small coding task, and then you need to code this and show your tutor that you're able to extend your assignment to with a simple additional task. And in the last line, if this is still readable, please bring your own laptop, and everyone in the team needs to bring their own laptop. So 3 laptops per team that everyone can code on their own the coding task. So this is individual then.
Yeah, so it's very similar to introduction to structured programming, your assignment interviews. Yeah.
Okay. Assignment 3. So if you register to the interview, you can do assignment 3 then. There will be a kickoff video available on YouTube today at 7 p.m. So you can watch it. You can also watch the video and then decide if you want to do the correction or assignment 3. And also same deadline in 3 weeks. But it's really cool assignment. So watch the video at least. It's a really nice extension, and it's as most freedom as you can get in our courses. Mm-hmm. Today in the evening after the practicals at some point. We will also write these things in an announcement again, and then the registration will be open. Oh, there is some nice thing. Was there more question? No, okay. One nice thing, visualization of assignment 2. I hope this is now somewhere here. I have prepared this already. Don't think about this code, but I just execute it and see what happened. So on the left-hand side, there is your game. And on the right-hand side, there is a beautiful version of your game. And now there is nothing. Maybe we need to type status. Status first. Okay, now the right-hand side knows what's happening in the left-hand side. So we can see the life and the mana and who is player 1 and who is player 2. And now also if we want to put something on the field, now this is this creature. Or maybe we need to look at our hands first. And if I type now creature, let's take the tutor maybe and place it on F4.
It's just the info.
Okay, and again, now I need to. Okay, yeah, I was tricked by the game. Okay, and if we type 2 times board, that it's refreshed, then also on the right-hand side we have that there is some evil tutor on the board. So this visualization will be available to you in the next few days. We need to release it. You also will get information how to execute it, but I think it's really nice.
Yeah, and I think it will also be very useful for A3, but you will then come up with your own stuff, but then the visualization might help you figuring stuff out.
Okay, I think that's enough preview. And then, any questions regarding organizational matters? So what happens now after assignment 2, or is everything clear so far? Looks good. So I think if we start with lambda function, then you take over. So lambda function, we discussed this the last 2 times in the practicals and were never able to finish it. Maybe just show the code that we have written there. So our main idea was that we can we can write these lines of code here, which is then called a lambda function. So we can store in this variable a function, which is then this part here, which takes parameters, has a return value, can execute stuff, and also has this capture block. And one example was that we have a function for each, which gets a vector of students and a lambda function, and then iterates over the students in the vector and executes the lambda function. So if we call the print student lambda, then for each of the students, this code would be executed. And then we also had an extension. We wanted to count the students, and we also created their lambda function. And this lambda function is now a bit more special because also in the square brackets there is something contained, which are called the captures. And this means that the variables that we specify here can be accessed within the lambda function. So the count is a local variable of the main function, and we can access the count here. And maybe first we had this that we don't have the end, we just wrote count, then we can only access count. So it's read only, but it's not mutable, so we cannot change it. And if we pass it now by reference, then we can also change the count value in the lambda function, although it's a local variable of the main. And so if we increase it for every student, then the count has then the number of students in the end, so the number of elements in the vector. Maybe also demonstrate this very briefly. Maybe we need to compile it. Ignore the warning. What have I forgotten? Oh, I'd return here an int. I should return a void here. Okay, sorry for that. So if I run this now, then we have 4 students in our vector, and with the print lambda, we always print the name of the corresponding student. And also with the count lambda, we start with 0, and for each student, we incremented the count, and we have a count of 4 in the end. So, and I think we have seen most of this with the captures. Just want to mention that you can also write an equal sign in the captures. So this means in the code we could write here, for example, an equal, and this means then that we can access all variables that we are also accessible in the main function, but only call by value. So this is just a copy here, so we cannot modify it. Or we can also write the reference operator here without a name. Then everything that's accessible in the main is also accessible within the lambda function, and we can change it by reference. Okay. And also there's a special capture with this. So if we write a lambda function inside of a method, of an object, or of a class, then we can also capture with this the object itself, so that we can also access the attributes of the object, for example. And I think we don't do this, but now we come to your coding part. So we have seen now how lambda functions work, how we can use them, but we want to do a bit more.
Okay, so to explain lambda functions a bit more, I wanted to somehow implement them on my own. So can I wait? Yeah, I will just comment this out, and then also here. Yeah. And now I want to somehow write a class which simulates these lambda functions for me. And well, we know, or we have seen last time, that we can also, for example, overload the function call operator. So this one here. And with that, we could implement something that's very similar to lambdas. And because our lambdas have one thing in common, namely that they always take a student reference, we even know how we can implement this operator. So what do I want to do? Well, I want to write a student lambda, which is an abstract class. Which needs to overload this operator here. And I need the virtual. So something like this. So what am I doing here? You can not only make methods pure virtual, but also operators. So you can say, okay, every class which derives from this student lambda needs to implement this apply operator, so this function call operator, and take a student reference for this operator. And what we could do now is we could implement our own student print lambda, which is a student lambda. And then in here, I'll just copy that. Implement for this operator whatever we want. So for example, I think here you did
I just printed the name.
Just some printing, like this. Okay, so how is this similar to a lambda? Well, we can now derive multiple of these classes and also write methods which accept student lambdas, and then we can pass different implementations of this student lambda, which all do different things. So now I can delete this. How they are similar, we can see now. I'll take this for each you already wrote. And if we look here, then okay, we get this vector, and we get this lambda, and we apply this lambda to the student. But now we know what type we want here. We just want to take a student lambda. And this student lambda is our abstract class. And we know this operator is supported by this class because we have it here as a pure virtual method.
So this is this operator with the brackets, then it just means, okay, I write the name of the variable and then brackets and the argument. So basically I don't need to use the dot now to access a method, but I just write the brackets there.
Yeah. And what we can do now is we can create this print student lambda. No, I think I call it student print lambda, yeah. And then maybe I call it the same way. I can use this for each function and pass in our print student lambda. Maybe let's try this. And yes, as we can see, we are printing all of those students. Okay, so, but now we have this class, and okay, we created this, and maybe if you think about the lambda function that we have here, for example, we can see that how we use this is very similar, because we have some variable here that we create, and this student, which is this of this type student print lambda. Just that with the lambda functions that we had before, we didn't need to actually create this class. Now, how would we do captchas? We still have this count here, and we want to count the students. So if I write a student count lambda, or maybe I copy this down here. I don't forget the override. Something like this. Okay, and here I want to implement something now. Does anyone have an idea how similar to the to this count lambda here, where we captured this count variable from the main, how we could now implement this for our custom lambda that I implemented with this class here. Like, we have this count here, and now I overload this operator. How could I access this count here within this class?
So you kind of need to bring the count into this class.
Yeah.
I mean, if you scroll down to the lambda function from before, we had this capture thing where we just wrote the end or the end and count to capture this variable.
I mean, I guess we could do something like this, but there is even an easier solution. Maybe it's too easy, so you think, no, that can't be it. But we could just store something like an integer reference to the count in our lambda class. And then pass it in when we construct it. So, yeah. And then here in the body, the same thing we do here, we just increase the count. And how this looks now is instead of using the square brackets here, when we create this student count lambda, we need to pass in a reference to the count. We can do this like this. And then down here, we can pass in our student count lambda. Yeah, and now this works as well. So somehow these captures that we have with the lambda is similar to the constructor that we call with our custom implemented lambda class. And this is because I think it is similar, because if we somehow, when we create this value, this variable, this lambda, in the captures, we just store these values with the lambda function. And this is the same we are doing here. Here we are not only storing what we want to do, but also the data that we want to have available while we do this. And this is the same the lambda function with captures does. It stores all of the captured variables with the thing that we want to do within this lambda function.
This is really nice view on how a lambda function could be implemented. And now the for each works completely the same as before. You have never changed the for each except for the data type, but if you would write out to there again, it should also work again, probably. Maybe let's try this.
Yeah, I think we need to keep the reference now.
Yeah. No, it doesn't work. You forgot one public in one class. Maybe this causes the problem.
I don't know why it's now with the... Oh, yeah, I know why it is.
Yeah, okay.
But yeah.
And now basically with this implementation, we did not change the for each loop, but it really worked for the default lambda functions, but also for your implementation of the lambda functions, which is really nice. Okay, I think let's move on and switch back to the slides.
Yeah, so now we're finally done with lambda functions.
But we will use them now. And yeah, maybe go to iterators and algorithms next. And now one motivation for this. So we have this for each loop from before. And the interesting thing about it was we passed the lambda function to the for each. And in the lambda function, there's the logic, which should be implemented in the for each loop. So only the for each just has like the construction that we need to iterate over everything, but what's then happening with every element is implemented in the lambda function, which is customizable as a parameter. So this is very nice. However, the other argument is not that nice in the moment because we can only pass vectors of students. Yeah, so if we look here, we have the vector of students. So the lambda function, the behavior is customizable. The vector is not. It's like this very strict vector. And yeah, I mean, we have templating as well, but we will show you something different now. But maybe just motivate iterators in this way. So I started with a very basic C array. A little bit of pointer arithmetic will follow. We just have a C array, and if we use the for each loop over the C array, we would write this code, integer I, iterating over the array, and then do something with that. And what is behind this for each loop, so that we can write it this way, is actually the following thing. We have a pointer to the array. And the pointer to the array means we have a pointer to the 0th element of the array, so it points to the 1. Then we do something with it, and then we increase the pointer by 1. And if we increase the pointer by 1, we increase the address by 1, and if we increase the address by 1, or actually by 4 in this case, because we deal with integers, but if we increase the addresses, then we move on to the next element in the array. Okay, for the next element, we dereference it, we can print it, we increase the pointer again, which produces the next element in the array, and so on and so forth. And so I started here, and if I take 1, 2, 3, 4 steps, this is okay. But if I try to take the 5th step, I would be outside of the array, and that's why I check if I am array plus 5, so like the 5th position, which is not present anymore in the array, then I should stop this for loop. Why do I say this to you now? Because an iterator works exactly the same. So if we take a vector and write this for the for each loop, where we iterate over the integers of the vector, standard for each loop, this actually looks like this. So we have the vector, and then here vector.begin is called, which returns an iterator pointing to the 0th position of the vector. So just for now, think this is a pointer to the element 1. Then we can dereference this pointer or the iterator to access the element and print it. And then in every round, we increase the iterator, or like the pointer in the previous example, to get to the next element. And we do the same stuff again, and then we iterate it over the vector. And now vector.end is exactly the position after the first position after the vector. So it would be the imaginary element 6, which is here missing. And if I would reach this element 6, then I need to stop the for loop because I already iterated over the whole array, or over the whole vector. And that is how iterators work. So what do we need, or what do we have? Seen in this example is basically a generalization of pointers, that we can use it with vectors or other data types. And allows to iterate over a container. Container means vector, deck, map, set, all those data types that exist within C++. Or you can even write your own iterator to iterate over some custom object that you have. And what was needed there? Some dereferencing, because we need to get to the element which is behind the iterator or behind the pointer. We need to be able to increase the iterator to get to the next element in the array. And we need to have some comparison operator that we know when we have reached the end. And this is what is needed for an iterator.
Yeah, so somehow this iterator behaves like a pointer. Because you can dereference it, increment it, and compare it. And this is everything we need to do with a pointer to iterate over an array.
And now the question is just how to get it, and we also see this, we have seen this before. So we need this begin and end method. So the begin method of a vector gives me an iterator to the first element, and the end method gives me an iterator to the element which would follow the last element. So this is the first element outside of the vector. Oh, okay, that's what I said. And this begin and end methods are also a bit customizable. So there's also a constant begin, constant end if you don't want to change the vector, or you can also iterate in the reversed way with a reversed iterator. So the begin would be the last element. If you increase it, you would go to the previous element, and our end would then point to the element before the first element in the array.
Yeah, so why can't you just swap end and begin to get the reverse iterator and then decrement it?
Yeah, because we have to shift by one, basically.
Yeah.
Because the end is always one element after the last valid element.
Yeah, and also the iterator doesn't need to implement a decrement operator.
This is also true, yeah. So it's only required that you can forward with iterators. Okay, now to our for each. So basically to this for each that we have in the code here. We could generalize this now, that we don't get the vector as a parameter, but we get an iterator where we want to start the iteration. We get an end iterator where we stop, and we get a lambda function. And now we just again iterate as we've seen it with the for each loop over the vector or whatever data type this is. The iterator always works the same. It can always be incremented, dereferenced, and compared to some other element. Well?
Yeah, so and again, we can think of just like passing pointers to our for each function.
Yeah, exactly, yeah. So keep this in mind now. I have now one more intermediate slide, and we'll come back to this idea in a minute. So what are algorithms? And this is very nice because there are already a lot of predefined algorithms in C++. For example, for sorting, finding an element, do some transformation so that each element is changed. And I mean, of course, it makes sense to use them together with some container, for example, a vector. And some parts of the algorithms are customizable. So in the sorting algorithm, it would be nice to customize whether an element is smaller than another element. Or in a find algorithm, it would be nice that we can specify which elements we want to find. And this part is customizable by a lambda function, yeah, which is a large surprise. No, hopefully not. And yeah, that's what we want to use now. We iterate over the vector without a loop. And why can we do this now? Because one of the simplest algorithms that is already implemented is the for each algorithm, which takes now as first parameter an iterator to the beginning, as a second parameter an iterator to the end, and as a third parameter, now this is here a function body, but this is then just a lambda function. So this is exactly the thing that I told you before. We have a for each function which takes begin iterator, end iterator, and a lambda function. And this is pre-implemented already for us. So we do not even need to write the for each function. You see this is in std, so this is already existent. So I can use this now basically. So if I have now my student list, or maybe I give me a reset to the previous version because I would like to start with my lambda functions. So here are back my lambda functions. So basically, I don't need to write this for each anymore. I just have my print student lambda. This is here. So let's get rid of this for each here. And just call std for each, which is already implemented. Student list.begin, student list.end, and the lambda function, print student lambda. Also get rid of those. Now, okay, it's not recognized. We also need to include the algorithm library. Oops. Okay. But now I can just call the for each from the algorithm, iterate over this vector, and print the student lambda. And now let's run it. Oops, this was not what I wanted. Execute it, and it works as before. For each student, the name is printed. And now this is also independent of the data type here. So for example, instead of the vector, what is your favorite data type? Maybe we take a DEC, which is a double-ended queue, include it. So that is some data type where you can append elements to the front as well as to the back. So in a vector, you can only add elements to the back, but in the DEC, you can also add elements in the front. I change the data type. Seems good. I always do the wrong thing. I compile it. I run it. It works again. Don't need to change the for each. I don't need to change the call. I don't need to change the lambda. I don't need to change anything. And if I write list, I hope that my constructor works. Include the list. And we have now a list, so a linked list in C++. Does it still work? It still compiles. We can still execute it. So it's really, it doesn't matter what data type we have here, what container we have here, this for each always works. Okay, now let's go back to the vector. And there are a few more algorithms also available, which are probably more interesting. And one is std transform. And std transform is also very similar to the for each, but we can really change each element. Yeah, okay, that's what I said. And so we can take the, for example, vector of students, then we modify a student and plug it into some other vector, for example. So we can take the students, and for each student, we can increase their grade by 1, for example, or decrease the grade to get a better grade. And then we do this for all elements in the vector and obtain a new vector with the better results of the students. So this works very similar again. So we call the algorithm std transform with the beginning of the vector, the ending of the vector, and if we want to put them into another vector, we need to specify also the new vector. So where we want to start inserting the modified objects. And again, a lambda function, where we need to specify how the transformation should work so that we decrease the grades by 1 to make the grades better. And this is also possible that we specify here the same vector where we want to store the objects in, so we can modify them in place. So we get the vector of the students with some grades, and for each student we update the grade to be better, and it's then contained in the same vector.
Yeah. So we just take each student, pass it to the function that we have here, and then store it back, and in this case into the same vector at the same position.
Maybe let's try this out as well. So let's get rid of this part here. So we print the students with the for each, and then we maybe call transform with the student list beginning, student list end, and then we directly insert it in the same list. Begin, and now we need a lambda function to customize the behavior. Now maybe we don't have, I don't think we have grades in the student, but we have a name and the set name. Maybe use that, maybe change the names of the students. What does the lambda function take? I mean, we iterate over the elements, so in each iteration, we get one element. So we get student reference student. And what should be done in the lambda function then? We get, for example, the name is student get name. And then we return a new student object with, what do we write as the name? OOP, OOP1 plus the name of the student and the same matriculation number. So this takes the student, takes the name, writes OOP in front, returns a new student with the updated name, and the new student is then stored into the student list. And now, don't need to write some function to print it, but we can just call the same for each again, for printing purposes. And let's see. And now we can see if we iterate the second time, here we always have the names OP plus the name of the student. And this is really nice. I mean, this transform function is used in many programming languages, also called a map function. And I mean, this is very common pattern that you need to use where you need to modify all elements in a vector or in some list. And there is also another function which is also very, very common, which is the filtering function. And in C++, it's called removeIf. Okay, it removes elements from a container. If a specific condition is fulfilled, and this condition is again customizable because we can pass it as a lambda function. And now what is the case here? We have a vector begin, vector end, where we want to specify where we want to iterate over, same as usual, and then we have the lambda function as a condition. Okay, let's try this as well. Now, in my data, I have now that David and Lucas have 0 in the matriculation number because they're not ordinary students anymore, because they're PhD students or even further. So maybe remove all those that are no real students anymore, so that have a 0 matriculation number. So we call removeIf student list begin. I cannot write, sorry. Begin, then student list end, and a lambda function which takes a student reference and returns that the it should return true if we want to remove something, so it should return true if the matriculation number is null. So we could, for example, return student get matriculation number equals null. So if it is 0, then we return true. Okay. And now we can print it again. We get some warning where it says, okay, the return value of the function removeIf is declared with no discard attribute, but unused result. So it tells us, okay, maybe we should consider return value of removeIf because we just call the function without taking the return value. But okay, maybe some weird warning. Let's run the code. And now we can see, maybe I remove this part here for better visibility, that this was the first print, and now in the modified print, we have Michi, Julia, someone without a name, and again Lucas, okay. But we still have 4 elements here. So maybe this removeIf doesn't quite work as we expected it. And the problem is this removeIf does not resize the container, but it just pushes the elements to the back that are, or that should not be used anymore, that are removed. And now we need to call one more function. We want to resize the container, so we call from the vector the erase method. And Again, this is based on iterators. So we specify a start iterator where we start erasing and an end iterator where we stop erasing. And so we vector or also any other container dot erase, and then we specify the correct range. And yeah, let's try this also here. So we need to know at which position we should start removing. And now this is the return value of remove if. So remove if returns us an iterator to the first position where we should start deleting.
So all elements that you want to remove, remove if moves them to the end of our vector or of our iterator. And then afterwards, we need to take care on our own to delete those elements that are at the end. And to know how many elements there are now at the end, it returns us this iterator to the first one.
So in our case, this would be, okay, the first two are good, they should be kept. And then remove if would returns us an iterator to this third element, which points to the third element, which is the first which should be removed. And then we simply call, okay, vector, and we have student list dot erase. And we start erasing at iterator, at the iterator. Yeah, this is already the pointer to this element, and we stop erasing at student list dot end. Yeah, because everything starting from here should be released. Okay, so we have this erase, and then we can print it, and now hopefully there are only two objects left. What have I done wrong? Unroot, but I use it here. I did not save. Okay. Okay, and now if we run it, we see, okay, there are only two elements left. The lambda function here in the for each is just called 2 times. So we really remove 2 elements and then resize the container to be of the correct size. Yeah? So in the remove if, all elements would be removed with a certain condition. So our remove is probably not the correct choice then, but you could, for example, use sdfind to find a specific element, which would again return an iterator, and then you could call vector erase. So maybe we say find returns an iterator, and then you erase from iterator to iterator plus 1.
Or with a quick hack, you could capture a variable as reference in the remove if, which you first set, for example, to false, and then only return the true to remove it if this variable is false, and then afterwards directly set it to true. So you only return true for the first element you find that matches this criterion. So you could also just implement it in the lambda function.
But probably this is the choice that is preferred. Yeah, so you can search for an element and then remove it. Okay, and I think this is enough for demonstration. Now let's see what is written here. Remove if returns iterator to the new end of the container, and then you erase from this iterator to the end, which we have done. So this is enough for demonstrating these functions, but let's have a quick look at 2 more of them, which you will need in the homework. So there is a sorting function, as already said in the beginning, where you can sort the elements. And so if you have 2 integers, it's very easy to compare them because one integer is less than the other. But what if we have 2 students? How is it defined that one student is less than another student? So we need to specify this behavior. And how can we do this now in the sorting function? We can, as we've seen this many times, we can pass a lambda function. So this compare, which takes 2 arguments, a and b, and then it should return whether a is smaller than b, in whatever sense.
Yeah, or a is in the sorted list, A appears before B. So it's the first element that it should be sorted before B. Yeah.
And another option is also available. You can omit this lambda function if there exists already a smaller operator for the class. Yeah, okay, because then we know how to write less than with these type of elements, and then we can just omit the lambda function, use this already implemented behavior. And one more function, std unique. Okay, let's say first like this. Maybe we would like to, or we have a list and there is duplicate data. Yeah? So there are many entries that are the same and we want to get rid of duplications and want to only have one element of each kind. So there should not be two elements in the vector that are the same after this operation. And std unique requires that duplicates must be next to each other. So if I have a list of 1, 2, 1, 2, unique wouldn't do anything because they are not consecutive. But imagine I sort them first, then I have 1, 1 and followed by 2, 2. Then the std unique would be able to see that there are 2 1s and there are 2 2s. Yeah, and then they are removed. So it sees, okay, here's a 1, the next element is again a 1, oh, it's the same as before, I remove it. And then
yeah, sorry. Yeah, so why is it weird like this? Maybe one reason could be that to remove duplicates, it would need to sort them first anyway, so it doesn't need to compare every element with every other element. And so maybe for optimizations, if you already know that your list is sorted, you do not need to sort it, and you can call this unique function without ever sorting it because you know it's sorted.
So it's more efficient than if you already have a sorted list. Yeah, so this is correct. Yeah, standard set is everything is sorted there, and also there are no duplicates. But now you get an input, maybe a list of elements or a vector of elements, and you want to work within this vector then, and you want to remove the elements there. So you could use sorting and unique, and then it's done. You could, of course, take all the elements, insert them into the set, then the duplicates would not be inserted, and then maybe transform the set back to a vector. This is also possible, yeah. But probably this is then more efficient because you don't need to put everything in another data structure and then turn it back.
So this basically is converted space-wise.
Yeah, this is true, and yeah. I mean, in the other case, you need to copy everything, and now you don't need to copy. Yeah. And now, okay, how can this be used? Okay, very similar to sorting. We either have a lambda function which tells if two elements are the same, or we have an equals operator already implemented for the data type that we are using here. And what happens now, it's a very similar thing to the remove if. We again don't have this resizing, but if an element is seen here, which is a duplicate, it's removed to the end, or it's moved to the end, but the size of the vector is still the same, so we need to again apply erase at the very end. Okay, so we have done this as well. Any questions regarding these algorithms?
Okay, so let's continue with ranges. But first, let's motivate them a bit. So what is the problem with algorithms? Well, this might be a bit dramatic because there's not a problem, but it might be annoying that you always have to write to like vector.begin and vector.end and pass those things to the function. But most of the time, we always need this begin and end. I mean, sometimes it's useful. Maybe we have a huge vector and just want to transform or sort some subset of this vector somewhere in the middle. Then, yeah, we can pass the begin that points in the middle and the end, which also points somewhere later. But I think really most of the time we just want to iterate over the whole vector. And now this can become a bit annoying. But thankfully, we have what did I do? Ranges. And what are ranges? Well, just like an iterator is everything that behaves like a pointer. A range is everything that can be iterated over. And what does it mean to be iterated over? Well, it means that it has such a begin and an end method. So every object that has a begin and an end method, so for example, a list, a vector, a map, a deck, is a range. And if you implement this on your own object, this begin and these end methods, then your object is also, your class is also a range. So how does this make our code shorter or more comfortable to write? Well, instead of passing this begin and this end to the sort function, with ranges we can just pass in the vector to the sort function. And we can pass anything here that has this begin or and an end method. Yes?
If we create our own data type and begin and end, does it work as well?
Yes. So it's really any type that has begin and end. How this can be implemented on the library side, we'll actually see later.
Maybe one question from my side. Is begin and end really enough, or do we also need an iterator then for this that we can that we can use begin and end?
You mean like, do we have any additional restrictions than just begin and end methods? Yes, there are some more technical ones, and also, of course, these begin and end methods do need to return an iterator. So something that behaves like a pointer. If these begin and end methods just return, I don't know, nothing or anything else, then of course this is not something that is a range. So we need meaningful begin and end methods for this to work. So, I mean, this is nice, but now we also said ranges and views. So what is a view? Well, a view represents a transformation of a range. What this means is, we saw this transform you had before, and a view is the same thing, not with iterators, but with ranges. And why they have a special name, we'll see shortly. So you can think of this, why it's called a view, because it's like of a different view of the same data. So with the transform, if we pass in the same iterator, we actually change the vector we're working with. Views only provide you a different view of the same data, so it does not modify any data that you have in your range, so vector or list. Yeah, and I think I want to continue with the live coding now. Where do you have it?
Here that ranges.
Oh. Okay, so we have this vector, and as we said, this vector has a begin and it has an end method, as we can see, and we can also see that it returns some iterator. So this vector is a range, and therefore we can use it like a range. We've already seen that we can do something like sort. I mean, this is already sorted, so we can do something like this. Ranges. Was it called sort?
Now you need to have you included ranges as a library?
Oh, no.
No, you have. Sorry, at the very beginning. No,
I don't know, does this need views? Or maybe, do you have C++20?
You compile the wrong thing.
Oh.
Ranges. Okay.
I'm not 100% sure what I forgot to include.
I will look this up for you. Maybe
Maybe it's something like this. No, maybe you can look this up. I'll continue with transform. So I hope this exists now. So we can transform views. We need to provide an input. Okay, it's also said that it does not have transform.
we will figure this out. Yeah.
Yes.
C++ reference says an header algorithm.
Oh, okay.
I also see this as well now. Yeah. So
Yeah, maybe. Thank you. Yeah, okay, now
it
this
works.
compiles. Okay, so you need to include algorithm. Yes.
So both ranges as well as algorithm.
Yeah.
Okay.
Yeah, and this sorts now our vector. Maybe we need this anyway. I'll print it. So iterate. Maybe I can switch the 3 and the 2. Let's see if this works. No.
It's the same as me before.
And yeah, the 2 and the 3 switched. Maybe I do not want this endless here, just like this. Yeah, so this sorted, and we did not need any begin or end. So let's look at the transform. And what I'll do here is we have this lambda function where we get every element and we need to return the new one. So for example, if I want to add 2 to every element, then I need to do something like this. And now this is in views, not in ranges, because this transform is this view now that we have seen before. Okay, the same thing again, yeah. And as we can see, it does not work now because with sort, it's a range. It was in the ranges library, so it somehow changed our original vector. But as I said just before on the slides, a view does not modify the original data, but it just provides us a view of the transformed data. So we need to somehow save this new view. I write auto because, as you can see here, the type is a bit more complex. But if we iterate over this new thing we get here, we can see that now we added 2 to every element in this vector, and we got a new view on this vector where every element is incremented by 2. But the original vector is untouched. And this also means that we can do some nice things. Because as you might have seen here, in this type, we have this transform view on a range, which is our vector. So actually this view is somehow, that this transform is somehow saved now in this +2. And what this allows us to do is creating pipelines, which means we change views together. And therefore we can use this pipeline operator, as we'll call it now. And how does this work? Instead of calling this transform like this, providing this input as the first argument, we can do something like this. This now might seem a bit weird, but you can think of it like we start with the vector, take this vector, and then like pipe it. So we send all of those elements into the transform, and this transform increments it by 2. Yeah, same result. And so why is this now nice? Well, maybe I format this a little bit different. Now, let's do it like this, so you can read it better. Now, I could, for example, then continue and send this into a new transform. It maybe I'll subtract 2 again or something.
So we should get the original vector again.
Yeah. So this now really allows us to chain these operations really easily together. And what is something else we can do? Maybe not transform it twice, we can also filter now, where we will turn true if we want to keep an element and false if we do not want to keep it. And for example, we could do something like this. So just keep even elements. And yeah, we can see that now we just got the even elements, but our original input vector is still untouched. So this pipeline we are creating here is really just something that transforms each of these elements. And one consequence of this, of how this is implemented, is that this also works with infinite views. For example, we have this iota with the number, which produces an infinite view starting at this number and then just incrementing by 1.
So iota 1 would be like our vector, but infinitely long. So it would start with 1, 2, 3, 4, 5, 6, 7. So it would contain all natural numbers, basically.
Yeah.
Which we cannot store, kind of.
But of course, if we have this view, we cannot iterate over all these elements. So with this take here, we can specify a number of elements we want to get out of this view. Maybe just try this. Instead of using this input here, yes? Mm-hmm. No, this transform just takes a value as an input and you return a new value that you want instead of the original value. So we increment every value by 2. So this 1 becomes a 3, this 3 becomes a 5. Yeah. Then we just take the even ones, and now we can also do this with this infinite view. Maybe I'll try to execute this. Yeah. We get many numbers because this never stops. So let's do what we had on the slide and just take, for example, the first 20 of those. And yeah. Now we have the even numbers starting at 4, 20 of those because we incremented each of those by 2. So now, why does this work? Well, this is something called lazy evaluation, where when we create this view, we do not iterate over all elements when we transform them. So this STD fuse transform does not iterate over all elements in our range, change the first one, change the second one, change the third one, but it just somehow stores in our pipeline that we want to apply this transformation. And then it stores, and then we want to apply this filter, and then we want to apply, this transform again. And what this does now is that at the end, when we iterate over our view, or we pipe it into this take function, it then just sends one by one those elements through our pipeline that we actually need. So if we have this vector and send it into our pipeline, then at this point here, those elements did not go through this pipeline. We just specified what we want to happen to those elements. And then down here, when we iterate over them, so if we have something like this, and then down here, when we iterate over them, we say, okay, we take the iterator, we want the first item, then the first item here goes through our pipeline, gets transformed, is filtered. Okay, we do not take this one, so the next item goes through the pipeline, is transformed, filtered. Okay, this one is even, so we come here and it is printed to the console.
So during the time we loop over the for loop, we then take the element in the vector, pass it through the pipeline, do the transformations, and once this is done, we print it. And then the next element gets run through the pipeline.
So for example, if we do something like this here, and exit out of the for loop after the first element here, then only we do not even send all of those elements to the pipeline. We only do it until we encounter the first even element after it is incremented by 2.
So we see the first 3 elements in the vector, and then we stop because we return in the for loop.
Yeah.
So it's different to the algorithms before, because for the algorithms before, we really said we do the transformation, we took the vector, we transformed all the elements. Then we took the next transformation, we transformed all elements, got the new vector. Then we did the remove if, so we removed the elements, they were shifted to the end. Then we erased them, we get the new vector, and then we iterate over this vector. But all elements were really changed during this process. But here, it's really only if we need them, we run the pipeline, we do the transformations.
Yeah, and this allows us to have infinite input, because we only process those who we actually look at. So those we actually iterate over or take here. Only those are sent through the pipeline. And another effect is that maybe if we have a huge vector and we do not even want to transform and filter this whole vector, but some elements of it, then we can create this pipeline, write here the whole vector, and if we then just look at the first 10 elements, then the vector is only processed as much as we need it.
Okay, I think that is that topic. We have 2 more topics regarding, or actually 1 large topic regarding templating. Should we make a break of 5 minutes, or should we continue? So who is for a break of 5 minutes? Who wants to continue on? Okay, everyone wants to continue on.
Yeah.
So the templating. So the next is probably already familiar to you. We have seen this in the lecture. So maybe go a bit faster on that. So what were templates? We could write a generic code. So we introduce the template parameter, which is then a type. And then we can, if we write a function which takes some type, then it can hopefully be used for any type. And yeah, the code is then only generated at compile time, because if we use this function which takes any type, C++ needs to see which type I'm using this function. For example, a student, and then, okay, it gets compiled for a student. So just move to the code example. How does such a function template work? We specify here the template parameter. So this is this t. This t is then a data type. And instead of writing here integer for the t, we just write generic type t. And yeah, we return the minimum. So we compare the elements and then return a or b depending on which is smaller. And as you can also see here in the main, we can call the minimum with 1 and 2, which are two integers. So this function, if we compile the program, then this function basically is compiled to where the t is replaced by integer. And then we also have the minimum called to characters. So this function is then also compiled to the special case of 2 characters. And if we run this now, okay, yeah, 1 is less than 2 and b is less than a, probably because this is a capital letter and this is a lowercase letter. So this works. We have one function, but it works now for 2 different data types, which is really nice.
Yeah. So think of the ASCII code. The uppercase letters come before the lowercase ones.
And maybe this is a bit awkward now that the b is smaller than the a. There exists the concept of specializations. So we have this generic function minimum here, which works for any data type t. But for this certain data type, I would like to have a different implementation. So in this case, maybe for the character, then we write template, but leave out the t, because we already know what our parameter is. It's a character. And then we write the function here for a character. So the return value is character. The parameters also need to specify here in the angular brackets. Now it's a specialization for characters. And now here we can do something different. So we do not just compare the characters, but we first convert them to lowercase and then compare them. This is a specific behavior. And now I can again call the functions. So this minimum function would then be the generic one. This minimum function, we have 2 characters, would be the specialization. And if I run this as well, then we could now 1 and the a, which makes maybe more sense that this is less than a b. But this does not only work with functions, it also works with classes. And this is now a very quick fix, because we had implemented our heap array at some point during the lecture. We extended it multiple times. And unfortunately, it only worked with integers. And now it's a very easy fix that it also works for a generic data type. And yeah, let me open it from the last time. So we have our vector. And okay, we can simply say, okay, we want to template it. So type name t. And now everything that is related to the integer data type should be replaced. So
just search for integer and replace with t.
Okay, so the length is always the same. Yeah, it should always be an integer. We shouldn't change that. But the array which points, or the pointer which points to the content, this should be now of data type t instead of just integer. When we get a vector, we get the length. Okay, the length, this should remain an integer, of course. But now we create a new array of type t on the heap. And then here in the copy constructor, we create again a new element of type t and assigning, okay, this works. In the copy assignment operator, which always needs to be implemented if the copy constructor is implemented. Okay, deleting works. Okay, here again, we need to replace it with the data type t, blah, blah, blah. Destructor works the same, get length. We don't need to touch this. If you use the add function, which returns an element, now the element which we return is not of type integer, but it's of type t. The index should still be a number, so this is fine. Comparisons is also fine. And also if we have the overloaded operator for the brackets, we have maybe a t here. Okay. Now I hopefully replaced every occurrence of integer which is related to the type with a t. And we also have a main function here. Okay, this doesn't work anymore because this vector as it is doesn't exist anymore. Because if I want to use the vector now, I need to always specify the data type in these angular brackets, similar to the standard vector that we are used to. Maybe let's use again a vector of integers and print the array with a vector of integers and initialize it with integers. So now this is again special data type, initialization, print array. Okay. Now let's see whether this still works. We are now in heap array. We want to compile and we run it. So what should happen? We initialize the array. So we should have the numbers from 0 to 10 inside of the array and print it. Let's see. Okay, this works. Okay, this is not so impressive now because we haven't done more than we have before. But maybe we can now create a vector of strings. Maybe make it, I don't know, size 2. And maybe we want to initialize also this array, maybe my string list. Print array. Okay, I mean, I cannot use these functions anymore because they only accept, if you look up here, vector of integer. So maybe we can also template those. Start with the initialize array. Maybe I can write just a t here and introduce before the template parameter t, type name t. So if I have now any vector of some type, I want to initialize it with this. Initialize array. Okay, this seems to work. Maybe do the same trick for printing. Template, type name t. So we print a generic array of type t now by printing all the elements. Okay. Nothing is read anymore, so let's compile it. And okay, it seems that it works out. I'm now a bit confused why it works out. I mean, I would expect now if I call initialize array with my string list, then this would be a vector of some type t, of type string in this case. And if I assign now an integer to that, I would have expected that it shouldn't work. Yeah, because I mean, this is an integer here. Where we iterate over.
I think the integer is implicitly cast to a character, and now you write the null character to the string.
Okay, so I can do this apparently. But maybe I don't want this behavior. Maybe I don't want to have like null here, but maybe I want to have some specialization here. Maybe that we write the string containing 0 and the string containing 1 here. So we can also do this with this template function. So I don't need the type name anymore. I have now the specialization to string. Here we already know that we have a string. And now I could, for example, make it like this, for example. Convert it to a string. Okay, now let's see it again. It compiles and it runs. And now in this case, we see in the string case, we again see 0, 1, because I mean the quotes of the string are omitted here in this representation. But we can use now the print array, the initialize array, as we were used to. Well, this is really nice. And now I don't need to write, for example, the print function multiple times for each type that t can have, but it can really generalize this now. Okay, maybe let me cheat a bit. I have something prepared. Do you see my heap array somewhere? Vector template, okay. Let's copy the student class. Assume we have a student class, I put it here. So the same student class as before. And let's get rid of the output operator for now. So okay, a very simplified student class, which has a name, which can be initialized with a string. Okay. Get rid of that. Okay. So maybe it is also possible to create a vector of my student now. My student list, maybe of size 1. Maybe I want to directly initialize it at position 0 with a student called, maybe something like this. Okay, so we have a list. The first element, Julia, is contained there. And now we print the array again, my student list. So, okay, print array. We have the function for printing the array. Everything seems fine. Let's see. Doesn't seem so fine. Okay. Short error message. Shortest error message ever seen. Okay. Doesn't stop. Okay, here is the error. Yeah, finally we reached it. Okay, and says invalid operands to binary expression, ostream, character, student. Okay, see out at this weird position I. 929, okay. Okay, but I mean, we only access the vector at position I and want to put it in the outstream. Why does this not work? Yeah?
Because the student class haven't had the operator.
Yeah, exactly, yeah. I mean, I kind of spoiled it a very little bit with that, yeah, but yeah, the student does not have an output operator, and we have a vector of students, and here we want to print then the student, and this can't work because there's no output operator, as you said, yeah? So then maybe let's don't implement it. I again cheated and copy it over. I think you have seen that before. You should know that. If I implement this operator now for the student, then I don't get an error, and the student is also printed. Yeah. So this is nice. Yeah. So we can work with that, and now also this print array function generalizes to a custom data type. But what was not so nice was this, if you remember, this very, very, very long error message where nobody really knew what's happening, unless you said the correct thing, but it's really long, and maybe this is then more involved because there are different types, and then it's like a template function that you have not written on your own, but is used somewhere else or coded somewhere else. So this is really ugly. And now, I mean, if maybe I could dream that there is a better option, that we get a better error message. Do you have something for me that we get, in this case, instead of this weird long error, something better?
Yeah. So what do we want to do? Well, our print array function works only for types that implement this operator. But we can pass in any types and then get this really long error message. So can we somehow restrict the template type just to the types we want? So just to the types that are really printable. And then maybe as a second goal, can we support any range and not just vectors? We have seen ranges, anything that can be iterated over. We want to be able to print anything that can be iterated over.
But maybe fix the error message first, if we can at least.
Yeah, and the solution is concepts. And what concepts allows us to do is that we put constraints on the types that can be passed to template arguments. And this concept is a set of constraints. So how does this look like? I think let's look at the syntax. Maybe this will become a bit more clear. So what we can do with concepts is to create one. First, we need to template it because this has to depend on some type. Then you write concept, the name of the concept, equals, and then requires. And here, this is somehow like a parameter list for a function. So we can write this template type here and then variable. And then here in the body, we just write all the expressions our type has to support. So for example, if we want our variable to be indexed with integers, we could write something like this. If we want that it overloads the plus operator, we write here something like this. If we want our variable to have a function called print, we can write something like this. And of course, we could just write requires and then some other concept that you already defined. So we can write some very complex stuff with this.
So basically, I could put in here the whole function that I want to execute, because then everything is included that my type needs to be able to do.
Yeah, more or less.
So maybe I could put in the print array function here, and then the output operator magically should be required.
Yeah, I guess so. But maybe let's just keep it to the things we actually want to do with the type. And how do we use this then? Well, there are 4 different ways how to specify those concepts. All of those do the same thing. The first thing is just writing requires, and then the name of the concept below the template of a function or class.
So this is now the case when I want to template a function, and then I write additionally to the template parameter the requires.
Yeah.
That ensures me that some operations are possible.
Yeah, and as we had this parameter for our concept, namely the type that we want to put these constraints on, we need to pass in again the template parameter that we want to fulfill those requirements. So for example, if we had some other type here, then we could say the name should be for T and for T2, or for T2, or we could say something, even do something like this and say this name concept should apply to both types that we have in the template. Yeah, this is one way to write it. You can write this requires also after the function. I think this is a bit weird. I would prefer this one. Then this is very nice if we just have one concept, which takes one parameter, then we can just write it instead of type name up here in the template. So if we write here the name of the concept and then T automatically is only allowed to types which fulfill this concept. And then if we write auto in a function, this is also templating. We can also write the concept before the auto to apply this to the template. Yeah, I would avoid templating with auto, and probably those 2 are the ones we'll use.
So 1 and 3. But this is very abstract now, so maybe we have an example, because maybe we can apply this to the print array directly.
Yeah. What we want to do now is create a concept which only allows us to pass types to this print array which are printable. So we'll template the concept and call it printable. So this is now a printable concept, and it has this one type parameter. We can now write requires Yeah, let's call it again variable, and we need a semicolon. Does anyone have an idea what we would need to write here so that that this printable concept only accepts types which can be printed to std out? Yes? So you said, for example, do a dynamic cast to some type. Well, the code you write here is never really executed. So the compiler only checks that all the expressions you write here can be executed with your type, but it never executes them. Yeah, we need to check that it has the operator overloaded, and one simple way to do is just write something like this. The compiler, if we use this concept, just checks, can we do this with the variable that has type t? And if the operator is overloaded, then we can do this.
So it's basically just a list of things that should work.
Yeah, you could also do, I think you could do something like this. Because this is the same thing. Right? No, this is not the same thing.
You need to put the variable. No.
What?
Operator. Do we need to call the operator less as a function with 2 parameters?
Okay. You mean like this?
Yeah, I think this should then work. So either of them is fine.
Yeah, but let's just stick to this one. So we just write in there what we want to work with our type, and then we can do here requires printable t. So now we require that our type is printable, that we pass into this print array.
So, but now this t is not related to above, right? So we could also name this above maybe s.
Yeah, or maybe let's just
or type, yeah. So
do something like this.
So this is our type, and below we say, okay, we introduce a template parameter t, which requires printable t, and printable t we have defined it before, so this output must be overloaded.
You could think of those concepts like functions that are executed while your program compiles. And what these functions do is just check if all those constraints you put there are actually statements that also compile. But they will never be included in your program.
Okay.
And now we also see the error in Visual Studio Code. So no instance of template print array matches the argument list. Okay. Maybe let's also check it here. And yes, the error is way shorter. We just see no matching function called a print array because constraints are not satisfied, because student does not satisfy printable. And I think this is now already very clear what our mistake is, and way more readable than the previous error message. And it even tells us which constraint failed. So this expression here does not compile.
So don't be sad. I mean, it still does not compile because the student still not has the operator for output. It cannot compile. So we cannot achieve that it now compiles magically, but at least we see in a much better view why it does not compile. And if you add now the output operator to the student?
Yeah, let's do this. So in here, if we comment in this output operator, now it works. So these concepts help us to get better error messages. I mean, okay, that's nice, but they also somehow convey something to someone else using your function. Because if someone else now looks at your print array function, you can directly see, okay, you templated this, but this function does not work with any type. It just works with types that we can print. And I think this is also nice. And concepts can also help us with a third thing we'll see later.
Mm-hmm.
I think the next thing I want to do, is maybe make this, let's make this with the accept the range.
Okay, so instead of just a vector, you want to accept the range now.
Yeah, so somehow two things, we need two things.
Mm-hmm.
The first problem is, how do we check if this template variable is a range? Well, we need, maybe let's call it R for range, or maybe call it something like this. Okay, this is a range. So we really want to accept this range here. But now, how do we check that this range is really a range and not just any template? And what do we write here now? Because we do not want to check if the range is printable. We want to check if the type we iterate over with our range is printable. And there are some built-in concepts we'll use now. The first one, link here I included just for completeness. Here are some concepts that you can use in your program. For example, same as accepts two types and checks if they are the same. Yeah, could be useful. But if we check the ranges library and scroll down to concepts, we can see there's this ranges range concepts that specifies that the type is a range. So maybe let's use that. So here we use this range concept and pass in our type. So this is a range.
Now you need maybe to include a real vector, because my vector is not the range, because I don't have implemented any iterators. Now you need to include the vector, my vector still for the student class. Don't remove it.
Yeah. But we can see now we already get an error because sadly our vector is not a range.
Yeah, so what does it tell now? Yeah, if you compile it.
Maybe let's look at the first one. No matching call to print array. Because constraints not satisfied, vector int does not satisfy range. Because we did not implement any begin or end methods.
Yeah, so if you scroll down a bit, here it states there is no begin.
Yeah, there's no begin.
Then maybe scroll further down, there is no, okay, again begin. Okay,
yeah, it just says it three
begin.
times.
Okay.
I think it just has us the first constraints that do not work out.
So I don't have a range.
Yeah, so maybe let's not use your vector. And instead use the std vector. And now it compiles again. No, it does not.
Yeah, you need to also use now the range-based for loop.
Yeah, now we do not have this get length, but we want to do something like element in my list.
Yeah, this should work.
And then here print the element.
But
then here we do not know if this is over integers, maybe something like this.
Okay, yeah. But now we have a range-based for loop, so range-based for loop, we can use the range here, and now it compiles.
Yes. But again, what happens now? I don't know what you're...
Control-Shift-7. But I don't know if you're in your keyboard there.
Okay.
So we removed it again, and now...
Yeah, and now we get again this error that says that if we find it...
Yeah. Okay, here.
That again says, okay, we can't print the element because, we cannot print our student.
Okay, so now let's implement that what we have seen before for the range.
So now how would we do this? How do we somehow get what value this range iterates over? Well, let's look again at CPP reference, and we can see that
I think you were at the concept already. So here they are.
Yeah, but this is not... Yeah, we need this one here.
Okay.
There exists these ranges, range value t, which is just something that is templated, that returns us the value our range iterates over. Yeah, maybe let's not think too much about it, how this might work, and just use it. Something like this. So this is how we get the type of our range. And now we want this type to be printable. Okay. Yeah, and it seems like our error now is again much shorter. And if we look at it, we can see the same thing again. Because, okay, now this might be a bit confusing. STD ranges range value t, vector, student, but it also tells us, aka, this is just our type student, does not satisfy printable.
Okay, so we can also do this.
Yeah, I closed the vector again.
And if we do this, comment this in?
Or maybe let's not comment this in. What I want now is, we have seen, okay, this is very nice with this printable, but what if I want to also support classes which just have a print method? Something like you wrote student, so maybe just, I know, something like print name.
Underscore.
I also want to support classes which can be printed like this. Then, okay, let's write a second print array. Like this, and maybe remove this because we do not want to support the output operator. And we want to be able to call print on this element.
I think you just want to call print because you already output in the print.
Oh. Yeah, not like this. Just something like this. And now, because we're working with concepts, how would you write a concept that specifies that this works? Well, let's call it function printable. And we want to require, now what do we want to write here? Does anyone have an idea? Yes? Yes. We just write variable.print because that is what we want to be able to do with this variable. And then again, like up there, we can do something like we want the thing that our range iterates over to be function printable. So we can use this range value t here to get the type our range iterates over, and then say that it should be function printable. And if we now compile, it works again. And we can also see that here, this print here is actually the print function. So this is also something that would not really be possible without concepts right now, because we have the same function with the same parameters, because it's just a template, implemented in two different ways. Without constraining the types up here to have the output operator, and constraining the types down here to have this print function, C++ would not know which of those two to call. And we can also see that if we uncomment the output operator.
So now both is there?
Yeah, so now we have a print and the output operator. Let's see what happens now. Now it says call to print array is ambiguous, because there are two functions where all of the constraints that we wrote here are fulfilled.
So because it has an output operator, we could call the first function. Because it has a print method, we could call the second function. But
yeah,
how can we decide now which is called? So this C++ does not do this for us, so there is an error.
And maybe does anyone have an idea how we could fix this now with concepts, that only one function is of those two is applicable if we implemented the print and the output operator?
Is there a way to say it's not, like it's not?
Yeah, yes, exactly. We can say we require our type to not fulfill a requirement. So we can say something like, we do not want it to be printable if we use the function.
You need the ugly
And
long thing. Sorry.
We need the parentheses around, yeah. Oh yeah, and we need this one here. You meant that one, right?
Yeah. To defer the time.
Yeah, maybe we can write this, split this up in 2 lines. Something like this. So we want this to be a range. We want the value we get, so the type of the value we get when we iterate over this range to be function printable, and we do not want it to be printable. So if I call this now print array with my student list, which one of those two functions is called? Maybe let's look like this. So our student list is printable and function printable, and here we say function printable and not printable, and here we just say printable.
Any ideas?
Yes. Yes, exactly. So the upper one is called because here we say we do not want it to be printable, but our student list is both. So the upper one is called because here we just have printable.
So then the output operator is called.
Yeah, and we see student, and student was our output operator. We could also try here, instead of doing it down here, in the second one, let's move it to the first one, and here say this is not function printable, So we have here it's printable and not function printable, and here we just have function printable. No, now we get an error. Why?
Because function printable, the concept is below the first time you use it. Same as always, if you have variables, you can only use them later on. So you need to define also the concepts before you can use them.
Yeah, and now we call the print function because we only use the output operator if a print function does not exist. So with these concepts, we have really precise control over with which types, which functions are called. And we can actually specify, okay, we want this function to be called if it's like that, and this function to be called if it's something else. And the order does not matter of how we define these functions. It's just what we specify here. And maybe just to make this a bit nicer, we can use the syntax that we have seen at the beginning and write the range template here instead of the type name to make this a bit shorter.
Okay. So the good thing is, now this was maybe a tough topic actually for the last 20 minutes in the last lecture, but if you do the homework, the exact same thing will be there, or slightly modified. So
it's slightly easier. You do not need to use anything from the standard library.
So you, I don't know, 11 people, 12 people have a large advantage for homework 3, at least for the last part. And I think this is a really interesting topic. We never taught this before. It's also new with C++20, but it's something that you already use, at least with respect to the error messages, because you profit from it when you code something. So it's a really nice concept.
Yeah.
Yeah, actually a nice concept.
Maybe just a quick recap. So concepts help us to have nicer error messages because we can specify what we want our types to have. It helps us. It helps other developers if we work with someone else to really see, okay, what is this template actually doing? So it makes the code more readable. And additionally, and I think this is the best advantage, that here we can really specialize templates function not only to one special type. So we could specialize before our print initialize array function to just integers and then initialize it with integers or characters. I think you had it. And here with concepts, we can restrict our template function to whole subsets of types. So for example, for everything that has a specific function or member. And this is way more powerful than just specializing to one concrete type.
Okay. And that's it. We saw all the list for assignment 3. Don't go over it one more time. I think it's enough. And we would like to thank you for being here also in the last practicals. It was very nice to teach the practicals again. I hope you had a good takeaway from it and learned a lot of things. And yeah, maybe you will see your tutor, at least in the assignment interview. There will also be then an event at assignment 3. But those which we do not have in our tutor group, thank you for listening, and all the best also for your next semesters in your studies. Thanks a lot.